A warm good evening to hi friends. In front of you is Surendra. Today I am going to teach you topic about hybridization. Before going to learn about hybridization, I will give this example of hybridization. In your daily life, you will see that mixture of two compounds. For example, salt, water, sugars. When we mix that, we will get a product. Like that only in chemistry also, in hybridization, when we mix two orbitals, we will get a compound. So that compound is known as hybrid orbitals. So for example, because in hybridization, we will discuss that hybridization. Before going to hybridization, we will see the objectives of the hybridization. So what is meant by hybridization? Hybridization is nothing but in order to explain the characteristics, structure, bond angle and its shape. Hybridization teaches about shapes, geometrical shapes and structures. And Pauli introduced that hybridization, the concept of hybridization to check and explain about the hybridization. Okay friend, okay guys, I will show you this slide of some key features of hybridization. In atom orbitals with equal energy undergo hybridization. So another one is that the number of hybrid orbitals formed is equal to the number of atomic orbital mixing, and it is not necessary that off-period orbital must participate, but in hybridization even completely filled orbitals with slightly different energies can also be participate. Hybridization happens only during the bond formation. So these are the key features of hybridization. So before going this, one more time we'll check what is meant by hybridization. So hybridization is nothing but the intermixing of two orbitals to give a new hybrid equivalent orbital is known as hybridization. So in hybridization there are many types such as Sp hybridization, Sp2 hybridization, Sp3 hybridization, Sp3 Dehydration, Sp3 D2 hybridization and finally Sp3 D3 hybridization. Every hybridization has some bond angles, its structures and its own bond formation. So we will discuss about it clearly and keenly. Okay guys. So first of all, in hybridization we are going to learn about Sp hybridization. What is meant by Sp hybridization? Guys, we know that what is meant by hybridization? The intermixing of two orbitals to give a new hybrid orbital is known as Sp hybridization. Like that only, Sp hybridization is also known as that the intermixing of one s orbital and one p orbital. It gives the new hybrid orbital of s hybridization. So in Sp hybridization, we will gonna teach you that Sp orbitals are oriented at the degrees of 180 degrees. It gives a bond angle 180 degrees. And in Sp hybridization, we will take a best example, beryllium chloride. Okay, why are taking only beryllium chloride? We will clearly tell in the theoretical part. Before going that, we also take a best example for Sp hybridization, beryllium chloride. So we taken the example of beryllium chloride. Beryllium chloride. So this is the beryllium chloride example. In this beryllium chloride, which is the center atom? Yes, beryllium is the center atom. So we will write the configuration, electronic configuration of beryllium. Why only we are taking beryllium? Because beryllium is the center atom of this hybridization. So we will write the configuration 1s2, 2s2. So here beryllium where Z equal to 4. So atomic number of beryllium is 4. So here we are writing that 1s2, 2s2. 2s2 is the outermost shell. So we will take the part in hybridization. Guys, I told you that beryllium chloride is the best example for Sp hybridization. What is meant by Sp hybridization? The intermixing of one s orbital and p orbital. But here there is a no participation of p orbital, there is only participation of s orbital. So when we take this, it's a ground state, it's a ground state, it's in ground state. While we go in excited state, while going excited state, what will happen? In excited state of beryllium 2s1, one of the orbital of s orbital electron is transferred to the 2px orbital. So here one s orbital and one p orbital both gives us sp hybridization, one sp hybridization. So in excited state, one of the electron from beryllium orbital is transferred to the 2p orbital of x orbital. So here two unpaired electrons are present. So after this we will also write the configuration of chlorine. What? Configuration of chlorine. Chlorine is the atomic number where equal to 17. So we will write the configuration 1s2, 2s2, 2p6, 3s2, 3p5. Okay guys, so here 3s2, 3p5. So in chlorine there is a unpaired electron in pz orbital. This is unpaired electron, one of the electron in pz orbital is unpaired. So this chlorine will be overlapped with hybridized beryllium. Here I will draw that this is the hybridized orbital of beryllium where it has unpaired electron. When chlorine gets overlapped with beryllium, okay guys, here this is the chlorine, this is the chlorine, is the hybridized beryllium orbital. So this two chlorine will be hybridized overlapped with linearly. It means finally it gives a shape So see these guys, chlorine is overlapped linearly to beryllium. Also chlorine in this side also it has overlapped linearly. So here which bond will be formed? Sigma bond will be formed. In between, sigma bond will be bonded with one s orbital and p orbital. Same here also sigma bond between s orbital and p orbital. So we can also write the structure of this. Beryllium is the middle atom where chlorine is bonded. Here chlorine also bonded. It gives the bond angle 180 degrees. Okay guys, this is the sp hybridization where two orbital, one s orbital and one p orbital both overlap with each other and gives the hybridization of sp hybridization. It's clear guys. So this is the process of sp hybridization. So we'll take a best example of beryllium chloride. Okay. So after this we'll gonna teach you that sp2 hybridization. Sp2 hybridization. We know that hybridization is nothing but the intermixing of one s orbital and two s orbital is known as hybridization. But in same sp2 hybridization also same, one s orbital and two p orbital is known as hybridization. So the intermixing of two orbitals, here the sp2 hybridization is the mixing of one s orbital and two p orbitals. The combination of these two atomic orbital creates three new hybrid orbital in equal energy. The new set of formed hybrid orbitals create trigonal planar. Bond angle is 120. So this is the Sp2 hybridization. Theoretically I will explain you how this chlorine will bonded with boron. So the best example we have taken in Sp2 hybridization is boron trichloride. In boron trichloride, boron is the hybridized center atom. So boron, we will write the configuration of boron where Z equal to 5. So the configuration of boron is 1s2, 2s2, 2p1. So where p orbital has only one electron. What we told that in Sp2 hybridization the intermixing of one s orbital and two p orbital is known as Sp2 hybridization, but there is only one participation in p orbital. So we have to intermix this. So where it is in ground state, we will go to the excited state. In excited state what will be happen? One of the electron from s orbital will be transferred to the py orbital. That time it will happen that one s orbital and two p orbital will intermix and gives us Sp2 hybridization. So after that we also write that Sp2 hybridization configuration of excited state. So in excited state, guys, what will happen? Two S1 and here 2p2. Why? Because one of the electron has transferred to the so here the bond between one s orbital and two p orbital, here the intermixing of one s orbital and two p orbital, this two gives us that Sp2 hybridization, we know that. So here what is happening in excited state, one of the orbital electron is transforming into s orbital to p orbital. So when boron will be the center atom, it gives that trigonal shape where linearly overlaps with chlorine. So we have that taken that example boron trichloride. So here 3 chlorine will overlap with boron which is hybridized. So here also we can observe that sigma bond. Why is the sigma bond is happening? Why? Because we know that when the atom will overlap linearly, that time sigma bond will be present. So here the sigma bond is between hybridized boron and between chlorine. Here also chlorine. So in this situation there is a overlap between boron and chlorine by linearly. So it gives the shape of 120 degrees. So bond angle in Sp2 hybridization 120 degrees and its shape is trigonal. Okay guys, so this is the process in Sp2 hybridization. We know that we learned here Sp hybridization and Sp2 hybridization. After this we are learning that Sp3 hybridization. So what is meant by Sp3 hybridization? This is very different. Why? Because in Sp hybridization and Sp2 hybridization there is a no present of lone pairs, but then quite different in sp3 hybridization. There will be most interesting topic. Why? Because in sp3 hybridization there will be introduction of lone pairs. Because of lone pairs there will be more bond angles will be decreased or increased. So we will give you example of sp3 hybridization of methane. In sp3 hybridization the best example is methane. Before going to sp3 hybridization, we will learn that what is meant by sp3 hybridization. We know that in sp3 hybridization the intermixing of an s orbital and p orbital is known as sp3 hybridization. But in sp3 hybridization the intermixing of an s orbital and 3 p orbital is known as sp3 hybridization. So in sp3 hybridization, when s orbital and 3 p orbital to form sp3 hybridized orbital. So here 4 orbitals are hybridizing, known as sp3 hybridization. The angle between this sp3 hybridization is 109 degrees. So 109.28 times degrees. Each sp3 hybridal has 25% of character and p orbital has 75% of character. So in this contribution there is only 25% of s orbital and 75% of p orbital. And example for sp3 hybridization is ethane. This is the best example. So in sp3 hybridization there are 3 types of bond angles and bond shapes. They are, first of all, in sp3 hybridization we are taking methane as the example. In methane we give the shape in sp3 hybridization. We taken the example of methane, CH4. CH4 is the best example for sp3 hybridization, where carbon is the middle atom. So it has a bond structure is tetragonal. So I will draw that So in sp3 hybridization the intermixing of s orbital and 3 p orbital to give the 4 hybridized orbital. So in s orbital, when carbon will take the configuration of carbon, in carbon we will write the configuration 1s2 2p2. So we know that intermixing of 3 orbital, but here there is the only contribution of p orbital is x, y, z, but here z orbital is unpaired. In methane z orbital is unpaired. So we have to transfer the one of the electron by excited state. So in excited state 2s1 2p one of the electron will be passed or jumped into p x, p y, p z. So one of the electron is transforming into pz electron. So here the intermixing of s orbital, here 1 s orbital and 3 p orbital. So it gives that sp3 hybridization. But here in sp3 hybridization I told you that lone pairs will be introduced. So when the lone pair will be introduced, we will be okay. So in methane the bond angle is 1 0 methane bond angle is 109 degrees 0.28. Okay, in NH3 it has a bond angle of 107 degrees 0.33, and in H2O water molecule it has 104 degrees. So why this three compounds will be related to Sp3 hybridization, but they are having different bond angles and different shapes, 109 degrees, 107 degrees and 104 degrees. So why? Because of lone pairs. Because of lone pairs, the bond angle and that shape will be changed. So in Sp3 hybridization, when lone pairs are introduced, that time the bond angle will be changed. What guys? Bond angle will be changed. So one by one we will discuss about that. In Sp3 hybridization, when lone pairs are 0, that time the shape is tetrahedral. The shape is tetrahedral. And another thing, when the bond angle decreases, the reason is nothing but in lone pairs the contraction of lone pairs will be decreased. So that wise the bond angle will be decreased from 109 to 107, 107 to 104. This will be happen because of lone pairs. Okay guys. So here in methane we will discuss that NH3. So NH3 it has one lone pair. How? So have a simple trick guys. This is introduced by me. I will introduce a simple trick to find the lone pair. If any compound having a lone pair, it will be very easily to find it. In JEE means that time we will lose the time in finding the lone pairs. But I will introduce a simple trick. By this trick I will find and you will find very easily. Simple guys, there is a nothing trick. It is very simple. We have to know that group names and we have to add them symbols. So nothing, nitrogen. So nitrogen belongs to, where Z equal to 7, nitrogen is belongs to 5th A group. So guys, it belongs to 5th A group. So 5th A group. So each group should we have to give a symbol like this. I will write this. Okay. Each group we have to take one symbol. For example, nitrogen is belongs to 5th A group. So we have to draw 5 symbols. Each in NH3 3 hydrogens are bonded. So we will give that each bonding. So why we have taken 5 X's? Here 5 X's are taken for 5th A group. Why? Because 5th group. So in 5th group we are taking this 5 X elements. So each of the X one will be bonded with hydrogen. Remaining 2 is belongs to lone pairs. Can you catching my point guys? Nothing but here 3 in NH3 3 hydrogens are bonded with one group. So this 3 are bonded and leftover excess elements are 2 here 2x equal to 1 lone pair. 1 lone pair. So in 2x 1 lone pair equal to 2x. So here 2x denotes that 1 lone pair. So in NH3 we are easily finding that it belongs to Sp3 hybridization. So we will count here 1, 2, 3, 4, 5 hybridized. So 5 hybridized orbital are present in NH3. So in 5 hybridized orbital 1 is lone pair and 3 are bonded with hydrogen. So we determinedly equivalently say that NH3 has a 1 lone pair. So because of this lone pair we have the bond angle decreased. We have decreased the bond angle to 109 degrees to 107 degrees. So we are easily finding that how many lone pairs are there in this compound by making of this formula. So it is very simple to find everyone. So because of this new formula trick, we are finding very simply. And another example, for example, in H2O, same process will be happened. So here also we will find that oxygen belongs to which family? Oxygen belongs to this belongs to 8th group. So we will draw that 8x's. So here we will give the bonding of hydrogen. So remaining two lone pairs. These two are lone pairs. So two hydrogen are bonded with one each group, and two XX are bonded. So two lone pairs are presented. So here two lone pairs and two hydrogen are bonded to hydrogen. So this gives that H2O has two lone pairs. Because of this, it decreases the bond angle of 104 degrees. So here guys, it is a simple formula which can be deal you to solve the how many lone pairs are there in any compound. So in Sp3 dehybridization, we have concluded that, see in this slide we can observe that methane has bonded with 4 hydrogen with a bond angle of 109 degrees, 0.28 times. In Sp3 hybridization, when the water molecule is bonded with two lone pairs, it has a bond angle of 104.5 degrees. So and also in NH3 I have told you that one lone pair, when one lone pair is presented, 3 hydrogens are bonded with nitrogen, that time the bond angle is decreased to 107 degrees, 0.28. So this is happened because of lone pairs, because of only lone pair, the contraction between two orbitals is been concentrated. So that wise that bond angle will be decreased. This is the reason why the bond angles are changed in Sp3 hybridization. So these are the example, these are belong to Sp3 hybridization. Next we will go to the Sp3 dehybridization. So in Sp3 dehybridization, there is nothing but hybridization involving the mixing of one s orbital, 3 p orbitals and 1 d orbital to form 5 Sp3 dehybridized orbital. Nothing guys, 1 s orbital, 3 p orbital and 1 d orbital to give that 5 Sp3 dehybridized orbital. So for this Sp3 dehybridization, we will take that example phosphorus pentachloride. This is the best example. Why? Because in potassium pentachloride, we will take this example in Sp3 hybridization. It has the shape of trigonal bipyramidal geometric structure, and it gives a structure and it has this bond angle of 190-20 degrees axially and overlap with 190 degrees. So this happened guys. So how it happened? In Sp3 hybridization also there are types of lone pairs. When it has one lone pair, it has one angle. When it has two lone pairs, it has different angle. So we will continually know what are the bond angles and what are the shape it has. In Sp3 hybridization, first of all we will take that example of potassium pentachloride. Okay, in Sp2 hybridization, the mixing of one s orbital. Okay, sir. So that in Sp3 hybridization there is nothing but the mixing of one s orbital and mixing of 3 d orbital is known as Sp3 dehybridization. Here we taken the example of xenon hexafluoride. In this hybridization, the intermixing of one s orbital, 3 p orbital and 3 d orbital. It means it giving the hybridization of s orbital, p orbital,
3 and D orbitals are 3. Okay, so this is the hybridization, guys. Hope you are enjoyed this. Lot of information by me. Okay, thank you guys.